Hi folks, we're going to take a look at page 419, number 12b. So what they tell us is that there's four forces acting on an object, and they want us to determine the resultant and equilibrium forces. Okay, so now there's a couple of ways to solve this problem. One thing you can do is take the forces one after the other and add them tip to tail. Okay, but I think there's something much easier. And here, this is where we use the commutativity and associativity of addition of vectors, meaning we can add them in any combination and in any order that we like. Okay, so what I'm going to do is I'm going to separate off the horizontal and vertical forces and add those first. Okay, now this is going a little overboard in terms of showing the work, but just to make sure everybody sees that this is valid. So if I look at the sum of just the horizontal forces, well, I take this, force of 30, and I add to that the force of 25 going east, and what I'm left with, well, is this vector 5 newtons going west, which I think we could have seen without actually showing the vectors themselves, but that's exactly what's going on. Same thing here. I take this vector 54 north, and I'm adding 42 south, so to that I add 42 south, and I'm left with this resultant vector at 12 newtons north. Okay, so in the end what we've done is we've reduced this to adding the vectors 5 newtons in the direction west and 12 newtons in the direction north. Okay, now in order to add these vectors, I'm just going to place them tip to tail here. So I'll move that 12 north vector there, and then the resultant is just going to be this vector here. Okay, so this is going to be my resultant vector, and easy to determine since we're working with a right angle triangle. Okay, so let's start with the magnitude of the resultant vector. So I'm going to be working with this here, and I see that it's just a right angle triangle since I'm working with west and north. So it's just going to be the square root of 12 squared plus 5 squared, which is 144 plus 25 is 169. Okay, and that's a nice perfect square, which is 13. Okay, now in terms of the direction, well, I'm going to find this angle here inside the triangle, and since this is the west direction, that'll just tell me how many degrees north to go. Okay, so I'll use tangent. I've got the 12 and 5, so we have theta is equal to inverse tan of 12 over 5. Okay, and let's figure that out here. So inverse tan of 12 over 5 is equal to 67.4 degrees. Okay, 67.4 degrees. So our final vector, our resultant vector here, is going to be 13 newtons. Okay, and this is going to be west 67.4 degrees towards the north. Okay, if you use the convention of using angles under 45, you would go north that many degrees west. Okay, but we also want the equilibrium force, okay, which is essentially just the force that counters this one here. So if this is the net force on an object and I wanted to stop it from moving, I would apply the equal magnitude opposite direction force to it. So it'll still be 13 newtons, so same magnitude, but now instead of going west 67 degrees north, okay, in fact, let's draw the vector up here. Okay, we're going to go east 67.4 degrees south. So this would be the equilibrium vector. Okay, so that's just going to be east 67.4 degrees south. Okay, and that's it for this one. So again, the way this works was to add these up in a clever order. In other words, the horizontal ones first, then the vertical ones, and then add together the remaining vectors. Okay, that's it for this one.